So example 4, a force F of magnitude 640 newtons is directed from point A. So this is a force in space, negative 143 meters to point B at 4, negative 2, negative 5 meters. So determine the components of F. So for the components of distance, you have to compute delta x, which is terminal point minus initial point. So delta x is 4 minus negative 1, so 5. Delta y is negative 2 minus 4, negative 6 meter. Then delta z is negative 5 minus 3, so negative 8 meters, delta z. So that the distance or the length of line AB is simply square root of 5 square plus negative 6 square plus negative 8 square. So F, remember, force X component is magnitude of the force, component of distance divided by distance. Fy is magnitude of force, component of distance along y, and over distance. Fz is magnitude of force, then z component of distance divided by distance. Or simply, force multiplier F over d force multiplier times the x component of distance, force multiplier F over d constant delta y, or F over d times force multiplier times delta z. Or another way is, remember that delta x over d is cosine theta x. So Fx is F cosine theta x. Fy is F cosine theta y, and cosine theta y is y component of distance divided by distance. Then Fz is F times cosine of theta z, and cosine theta z is z component of distance divided by distance. So distance is square root of 5 square plus negative 6 square plus negative 8 square. So distance is 5 square root of 5 meters. So substitute into the formula, Fx equals 640 times 5 over 5 over square root of 5. So Fx is 286.2 newtons. Fy is 640 times negative 6 over 5 over square root of 5. Fy is equal to negative 343.5 newtons. And Fz is 640 times negative 8 divided by distance 5 square root of 5. So Fz is negative 457.9 newtons. Then let's also solve problems as an exercise from your handout that I uploaded. So this is the first, to find the moment of the 360 Newton force about A. So let's solve this into two ways. One is the direct method, the other one is the Varignon's theorem. So first, for the direct method, remember that the angle between the vertical and the incline, so this incline must be perpendicular to the distance, perpendicular distance. So the angle of inclination of the perpendicular distance therefore must be equal to 10 degrees also from the horizontal. So this is the horizontal, this is the inclined or the perpendicular distance. This is 10 degrees because that's also 10 degrees. So therefore this angle here is 20 degrees. So that's 10 degrees, this is 20 degrees. So since 1.2 is given, the hypotenuse of this right triangle here, the perpendicular distance is 1.2 cosine of 20. Remember, this is 20 degrees. So moment, therefore, of 360 Newton force about A is 360 times D, and the perpendicular distance D is 1.2 cosine of 20. So that's the direct method. 360 times 1.2 cosine 20 degrees, and the sense is clockwise. The moment about A is 405.95 Newton meter clockwise. So for another method, let's have the component for Varignon's theorem. So let's resolve 360 into components. The horizontal is 360 times sine of 10, opposite, which is horizontal. So 360 times sine 10. The vertical component, which is downward, is 360. Because it is adjacent to 10, so 360 cosine of 10. So that the The horizontal distance or the moment arm of 360 cosine 10 is 1.2 cosine 30, which is this, and the moment arm of 360 sine 10 is this one, is 1.2 sine of 30. And both components are, so 1.2 times this moment arm, the moment arm tends to rotate clockwise, so clockwise. 360 cosine 10 times moment arm 1.2 cosine 30 is also clockwise, so we should add the moments. So MA is 360 sine 10 times 1.2 sine 30 moment arm, that's clockwise, plus 360 cosine 10 moment arm 1.2 cosine 30, and it is also clockwise. That's why we add. So the value should be the same as this, 405.95 Newton meter clockwise. So that proves that Barrington's theorem is effective, especially when the moment arm is not easy to solve. Although it's only 3 to, that's very easy. For this situation here, uh, we have to compute the moment of this 150 Newton force about A. So we have to extend the line of action of 150 by Barrington's theorem. Remember, we can do that. And the angle between 150 and the vertical is 22. So therefore, the angle between the line perpendicular to the force must also form an angle of 22 with the horizontal. So this is the distance, direct distance. So I'll call this point E. So distance AD is 1.6 plus zero point 0.7 is 1.3 square plus vertical 0.9 square. Distance AD is 0.5 square root of 10 meters. So extending, so this is the right triangle now, and this angle is 22. We can also add the angle here, which is the angle of this red line with respect to the horizontal is arctan of 0.9 over 1.3, or tangent of this angle is 0.9 opposite over adjacent, 1.3. This angle is 22 degrees, just like that. So theta A is 22 degrees plus arctan of 0.9 over 1.3. So the total angle at A is 22 degrees plus arctan of 0.9 over 1.3, 56.695. So the total angle there. And this perpendicular distance is distance AD cosine of 56.695. So moment about A is 150 times 0.5 square root of 10, that's the distance, times cosine of 56.695. So moment about A is 130.23 Newton meter clockwise, because counterclockwise, because if you drag this moment arm in that direction, this will rotate counterclockwise about A. Then by Barrington's theorem, let's resolve it into components. This is 150 sine of 22. The vertical component is upward 150 cosine of 22. So the moment of 150 cosine 22 is counterclockwise about A, while the moment of 150 sine 22 is clockwise about A. So therefore, let's write 150 cosine 22 first. Its moment arm is 1.3, 0.6 plus 0.7 as positive. Then minus 150 sine 22, the moment arm is 0.9, so negative. So 150 cosine 22 times 1.3 minus 150 sine of 22 times 0.9. So solving for MA is the same, and the sense is counterclockwise. So that's it.